Okay, hello everyone. Today I'm going to be talking about featurization, which is a machine learning algorithm that allows you to find correlations in complex data that you wouldn't be able to see with the human eye alone. So the power of our supercomputers has grown exponentially since their conception, but not only have the supercomputers grown, but also has the computational power to the average scientist who is doing large data manipulations and wants to understand their data better than they could with the human eye alone. So today I'm going to talk about a method called featurization, where you can use machine learning to break down this data. And it splits into 3 steps, where you have to define a problem that fits within your parameters, turn your data into features that can be suitable for the machine learning, and then leverage your results in a way that you couldn't have before. So first you need to define a problem that works for this type of analysis. This can be any type of numerical output of interest, so one single numerical variable. So for example, you could think of ad clicks per dollar spent advertising on Facebook, or you could think of any of the things up on the board, but specifically today I'm going to talk about the binding energy of CO2 for different specific materials. So you can think about your data set as having different samples with one output of interest, and if you can do that, you can put your data into this type of machine learning algorithm. Next, you need to turn your individual data or samples into features. Features are just unique numerical identifiers that can help separate the different samples and correlate ultimately with your output of interest. So really what's most important about these features is they need to be simpler than your target output, so you can gain correlations to the emergent property you're interested in. These features are often unique numerical identifiers that are very simple, and you can calculate them or just observe them without having to do a full study like you would for your output of interest. And finally, you can leverage your results using these techniques, doing something called feature importance. You can find which features are most correlated to your output, and you can also predict the output of new data by taking your samples or taking a new sample, putting it into your trained machine learning algorithm, and then you can predict the output for something you haven't done the study on. So today I'm going to talk about a specific example using this method about finding better CO2 catalysts. Now, I don't have time in 8 minutes to belabor how important it is to find materials that can help us control the CO2 in our atmosphere, but instead I just want to talk about a specific way we use this method to help find materials to help us do this better. So in addition to just turning CO2 into something else that isn't in our atmosphere, we want to turn it into highly valuable products. So here you can see that multi-carbon products are the most valuable and energy dense, so that's what we want to turn CO2 into, if at all possible. And previous work has shown that copper metal is uniquely apt at turning CO2 into these multi-carbon products. However, copper metal by itself isn't very good at binding CO2, so we want to help find new materials that are similar that can bind CO2 and still have the same conversion properties that copper does alone. So attacking this problem, we took inspiration from this biomolecule on the left, which is an enzyme in plants that helps bind CO2 strongly. So this enzyme works by having 2 metals, iron and nickel, in a very local chemical environment that allows it to bind CO2 strongly. So we thought, let's replicate this in the surface of copper. So by including 2 different dopants, taking every possible element on the periodic table, putting it into the surface, and trying to see which ones can improve our response, and then using machine learning to understand why certain ones are better than others. So to make our data set, this is exactly what we did. We have individual samples that are materials that are just 2 different dopants into this system, and then we calculate the binding energy using first principles methods that are used in my group. By doing this, we can generate a massive data set that we wouldn't be able to just look at and understand the correlations, so we need to use this machine learning featurization analysis to understand the trends we're seeing in our data. So what I'm showing you here is a lot of data points. Each one of these data points is one of these specific materials, one of my samples, and the x-axis here corresponds to the binding energy of that sample. So farther to the left is better. The line on the right is just what copper is by itself. So a lot of these are better than copper. And then the y-axis is just how makeable these materials are. So lower is better, but for our machine learning analysis, we're only focused on the x-axis, and then the y-axis comes in at the end when we're doing our analysis of these samples. So now that we have our data set, we have all of these different materials with the binding energies correlated, we want to turn our individual materials into machine learning features. Now again, these features are just unique numerical identifiers. that need to be determined by someone who is an expert in the field. Anyone who's doing a different type of study would have to figure that out for themselves. But using our chemical expertise, we decided to make the identifiers, the dopants, just the unique different characteristics of the individual atoms. So just looking at the periodic table, we assign the mass, atomic number, place on the periodic table, the effective charge, all of these simple things to calculate for each individual atom that we can then correlate to the binding energy, which is a much more complex calculation. And we take the summary statistics, minimum, maximum, average of these different features to correlate to the minimum, maximum of these unique atomic identifiers to be the features that we correlate to our binding energy of interest. So here I'm showing some results for that data set. This was based on over 400 tested materials, and we found that the maximum charge between the two dopants, whatever one of these two materials is whatever one of the two dopants is most highly charged, correlates most strongly with the output we're interested in, with the binding energy. So you can see that once we hit a minimum threshold of having at least one of our species be very highly charged, we know that means that it can bind CO2 strongly. So we want to be able to put one highly charged dopant in there. But it's the maximum charge, not the average charge between the dopants. So we know that we only need one of our two dopants to be highly charged. This plot on the right I'm showing you, these blue materials just correspond to two materials being highly charged, and the orange correspond to having one. That means that if we have one highly charged material, one highly charged atom in our material, then we can have a makeable material, have a lower formation energy, and this material can bind CO2. So this is insight we were able to gain only using machine learning featurization. And this is exactly what I'm showing here. We were able to identify seven new materials that can bind CO2 more strongly than copper, but keep the characteristics of copper that make it such a great CO2 catalyst. So we hope that the next step of this project is to find some experimentalists to make these for us, but we were able to gain the insight into what makes these specific materials better than others using this machine learning featurization. So finally, I just want to leave you all with the thought that this type of analysis is not just something for this specific project. Featurization can be used for any type of field. So you just need to be able to have a large data set that's split into individual samples that have a single numerical output of interest, and you can use these same machine learning algorithms that are widely available in Python to figure out what are the most important things about your individual samples that make it good for your output of interest. Big data is really powerful, but it's on us to leverage it in the best way possible. Thank you for hearing my talk today.